Hello, I'm Mr. McChesney, and today we're learning about diffraction gratings. The problem we have here is a student noticed a beautiful spectrum reflected off a rented DVD, basically a rainbow. She directed a beam from her teacher's green laser pointer at the DVD and found 3 bright spots reflected on the wall. The label on the pointer indicated that the wavelength of the laser was 532 nanometers. The student found that the spacing between the spots was 1.29 meters on the wall, which is 1.25 meters away. What is the spacing between the rows of the DVD? So diffraction grating is a thing that has many little lines on it very closely spaced, maybe as many as 10,000 lines per centimeter. And it causes light to break up into little patterns like we see here. So what we've got is shines the laser at the DVD, one beam comes off and hits the wall at spot 1. And then it gets split up also so that it hits the spot 2 and also spot 3. And if you had a big enough wall, you might be able to see a couple extra spots. So we can measure the spacing between the spots and how far the DVD was from the wall. So let's write our known and unknowns. So we start with X, which is the spacing between the spots, which is 1.29 meters. And then we also have the length we were from the wall, L, which was 1.25 meters. And then we also know the wavelength of our laser, which as always, you never want to point at someone's eyes, especially if it's a green laser. And that was 532 nanometers. So what are we looking for? We're looking for the angle between the bright spots. So we know that we've got a right triangle set up here that has side L and side X, and we're looking for this angle. So in order to find that angle with a right triangle, we're going to use the first bright spot there, and since we've got the two sides opposite and adjacent of the triangle, we're going to use the inverse tangent function, which on your graphing calculator would normally be something like secant tangent. So that is the opposite side X divided by the adjacent side L. So if we plug our numbers in there, theta is equal to the inverse tangent of our numbers. X was 1.29, and again, whenever doing problems with tangent, cosine, and things like that, check to make sure your calculator's in degrees, because your math teacher likes to put it into radians. And we're going to divide it by the length from the wall, 1.25 meters. So that's going to give us an answer of 45.9 degrees. Now, is that answer reasonable? We've got two sides of a triangle that are remarkably close to each other. So that's almost like the sides are the same size, and if that was the case, we'd have a 45-degree angle. Here we're just slightly off, so we have slightly larger than a 45-degree angle. So that makes sense. So the next part was then solving to find out what's the distance for the diffraction grating. So we're looking for D. So we don't know what that is. If you look back in your book, you'll see you have a formula that is, let me not jump ahead of you here. We have a formula that is the wavelength of your light is equal to the diffraction spacing times the sine of the angle. So I want to get this where I have the D by itself, which is what we're looking for. So I'm going to multiply both sides, or divide by 1 over this, divide by sine, or multiply by 1 over sine, and that's going to cancel out the signs and give us what we want, which is distance between the grating there is equal to the wavelength divided by sine of the angle. And that little symbol I drew is actually a Greek letter lambda, and that stands for wavelength. So we know it is 532 nanometers divided by the sine of the angle, and I should write the angle in there that we just discovered, which was 45.9 degrees. And a lot of times, kids, you'll just solve it right as that, but if we look back, we've got meters and meters as our other answers, so we want to put our answer for this into meters also. So I want to convert the nanometers into meters. So if I do that, 532 nanometers, I go back to the beginning of your book where it talks about dimensional analysis, and I want to get rid of nanometers, so I need to multiply by 1 nanometer is equal to 10 to the negative 9th meters. By doing that, I got nanometers on top of a fraction and on bottom, so if you divide something by itself, it cancels out. We have 532 times 10 to the negative 9th meters. And I really should put that in the correct notation and scientific notation, which is get the decimal place over 2 spots. So that would give me 5.32 times 10. I moved it 2 spots to the left, so my number gets larger by 2. My exponent gets larger by 2, which would make it 10 to the negative 7th meters. So if I come back up, this is going to be 5.32 times 10 to the negative 7th meters. Haven't done anything to the bottom, so it's still sine of 45.9 degrees. And you always want to have your units on there. So if I do that, I get an answer that's 7.41 times 10 to the 7th to the negative 7th meters. When you take sine of an angle, you get a number that's unitless, so we're taking meters divided by a unitless number, which gives us meters. Sine of 45 should be a number that's smaller than 1, which means it's going to end up multiplying or causing our simple part here to become larger, so that's why it's 7.41. So our final answer to this is 7.41 times 10 to the negative 7th meters.